Hello everyone, my name is Hao Peng. I got my PhD back in 2014, so it's a long time ago. And I have been working for iCanco and Additive 3D for a long time. And today I will give some you introduction about this company Additive 3D and also the software name of our product. And I'm the vice president of the product development. So if you have any questions, if you are interested, just let me know. So there are lots of additive manufacturing process right now, and we can categorize them into different types. For example, the material extrusion-based additive manufacturing. For example, the direct energy deposition process. For example, the sheet lamination process, and also the powder bed filler process. Additive 3D can work for all of those, basically any layer by layer additive manufacturing process. However, for our research right now, we focus on this area, the powder bed filler process. For those who are not familiar with the powder bed filler process, here's the animation. So it shows how a rocket motor throat built additively and layer by layer in this process. And for each build cycle, you can see that first the recoater blade will apply a new layer of metal powder, and then the laser will selectively melt some specific region, and then the powder bed platform will move up, build platform will move down, and the next build cycle will continue. And this EOS M290 machine is a very popular powder bed filler machine, and we have one in iCanco. There are lots of applications for the powder bed filler process. For example, automotive, biomedical, and aerospace. However, there are also lots of challenges. Because every time you use laser to melt the metal powders, the temperature can go up high to 1000 degrees C. That's caused lots of temperature gradient and cooling rates. And that's why we have lots of thermal distortion after you print the part. And due to the same reason, you have lots of stress between layers, but that's why you have layer delamination. And sometimes you even have the crack formation at micro scale. This is a story happening in iCanco. So when we try to print this pattern, we choose this horizontal build orientation in the very beginning and try to use this strong support to hold it down to the build platform. And finally, we got this problem. You see that at this corner, you got some delamination, and after this delamination, the distortion will be very large, and the recoater blade try to collide with the part, and finally, we got a failed build. So this problem is very common in the 3D printing process. And there are lots of software tools trying to solve the problem. In the first step, they try to generate STL files with some CAD model. And then they try to choose one orientation based on their experience. And then they will generate the support structure for this orientation. And they want to know how much distortion I will get. So they put those orientation and support structures into a simulation software. And finally, they go through this iteration process. So they go through this iteration process and finally find one orientation they think they will give a minimum distortion. And this iteration process may take lots of time, lots of money, and finally they will find one orientation they think is good, and then they put that orientation into the printer and try to print it. However, based on statistics, we still get about 40% failure in the build. So Additive 3D is designed to solve this problem from a different way. You can see that we are trying to develop this optimization loop. And for each optimization, we try to change the orientation automatically in the software, and we generate support structures automatically. And finally, we use a physics model to try to predict how much is distortion, how much stress you will get from this orientation and from those support structures. And after going through this about 100 orientations, we will finally choose the one give you minimum distortion. In order to accomplish this, the one key part is here, business model. We want to make sure it's fast, it's reliable, and it's accurate. Here's a literature review about the physics models in the market. Based on the simulation domain and also the computational time, I categorize them into this mesoscale model and also part scale model. Example one is the example of the mesoscale model. Simulation domain is very small, it's less than 1 millimeter, it's a very small area. And we try to model each single metal powders and also the dynamics of the melt pool and also the capillary force between the liquid metal and the metal powders. And it's very accurate, very in detail. However, you can see that it takes almost forever to compute it, even with parallel computing. Example 6 is another is a part scale simulation model. And you can see that this part the size is only 5 millimeter, not very large. And they use finite element model to simulate it and try to get some distortion information. However, it also takes about hours to compute. So those models are not feasible for our application. Our goal is about here. We want to simulate a part around hundreds of millimeters, but within just a few minutes. So that's our goal. We don't have a solution in the literature, so that's why we developed the code ourselves. We developed a new method. This method is called thermal circuit network method, or called TCN. This is the basic idea. You see that there's a part here. We slice it into layers. Here I just slice into 8 layers. But in real application, we may use more layers to get more accurate results. And for each layer, based on the geometric configuration, we will develop a network of thermal capacitance and thermal resistance for this layer. And then we will assemble the network for each layer into a global network. Same for the support materials. We have support here, here, and here. We also build those thermal capacitance and resistance for those support structures, and we build this into the part network. And finally, we use this TCN to model the layer by layer build process and try to predict the temperature information. And here's the example. We build the part in 2 ways. First, horizontally, second, vertically. And you can see that for this horizontal part, the temperature gradient is much larger because the cross-sectional area is larger, and heat is more easier to dissipate from top to bottom. For the vertical part, you can see that we have an overhanging region. That's why when you build layer to layer to this part, you will see that temperature at those overhanging region is much higher, and you can see how temperature will dissipate from this overhanging region to these neighboring regions. And this is the comparison between the TCN method and the finite element method. For this horizontal part, it takes about 2 minutes for this TCN and about 14 hours for finite element. For vertical part, 18 minutes for TCN and 41 hours for finite element. We only sacrificed about less than 15% accuracy, but we achieve about 2 orders of magnitude speed instead. So after we get temperature information, we try to get how much distortion we get. So that's why we developed this quasi-static thermomechanical process. We call it QTM. And this is the build process in additive manufacturing. First step, we use laser to melt the metal powders. Step 2, the melt pool will cool down by steering liquid phase. Step 3, temperature keep dropping, but this time the top layer is in solid phase, and further temperature drop will will cause lots of thermal stress in the part. 1, 2, 3 will iterate in the build cycles. And finally, you get a part and you want to remove it from the build platform. That's why you will see lots of distortion. We call this process stress relaxation. And this is the corresponding temperature profile in this process. Because the build process is very long, sometimes it's a few days, the stress accumulates in a very slow fashion. And that's why we can model this process as a quasi-static process. And we only care about temperature from the beginning of this build cycle to the end of this build cycle for each layer. We don't need to, we don't care about all the temperature history here. In this way, we can make our QTM very fast. So this is the comparison between our simulation results and also these experimental results. Experimental results are in these blue rectangles, and those are simulation results from our software. The experiment is performed by Lawrence Livermore National Lab, and they use this digital image creation method to measure the X, Y, Z displacement after they remove the part from the build platform. They build the part in 2 ways. First, horizontally, second, vertically. And you can see that our prediction is very close to the experimental results, both qualitatively and quantitatively. And the material is 316L in steel. So after we get this QTM and TCN to work, and we can get the thermal distortion value very quickly, and we can perform our optimization loop we talked about earlier. The optimization method we are using is called direct method. This is the method in literature. If you want to know more about it, you can go to this reference here. This one is a pattern search method and non-gradient method. So this one is sampling different orientations and try to find what's the better solution in the next optimization loop. We only optimize the orientation about X and Y. We don't think, we assume the rotation about Z has no effect on the thermal distortion. After we optimize X, Y, we will rotate the part about Z to make sure the part grows away from the recoater plate. It's very important. So a short summary. The goal of our company is to develop this optimization tool, which can give you the best orientation and also the support structures. And in each of this optimization loop, we will change orientation, generate support, and use this TCN and QTM to predict distortion and thermal stress. And finally, we'll give you the best orientation and support. And you can download all those files, STLY files, CLY files for your printer, and then you can start printing. So after we develop all those algorithms, we try to give you a very nice user interface. That's why we develop a web application. So this is the user interface of the web application. After you create username, password, after you log in, this is what you see. Left side, this is the file panel. Right side is the job panel. You only need 3 clicks to create a job. You upload the STL file you want to print here, and you click create job. And then you will put what materials you want and what printer you are using. And if you have some advanced options here, you can input what's the laser power, laser scanning speed. But we set some default values for you, so most of the time you don't need to worry about those. And then you will use Sunata in tangents. And then the third step, you just simply choose you want to minimize the distortion, and then you can start the job. So here's the results you will get. The right side is the results panel. So after you click each job, it will expand it for you. And you can see that even though you choose minimum thermal distortion, we also give you other 3 options. Minimum support removal, minimum support volume, and also the minimum build time. And you have all those 4 options to choose from. And after you spend these optimization results, we will give you the result for the support structure and also the oriented part. You can download all those files. And we have another option here, it's called estimate build cost. It will show you how much time it takes to print the part, what's the material required for this part, and you can put your overhead there and you can give a nice quote about this job. And if you want to know what's the distribution of the distortion, what's the magnitude of the distortion of this view orientation, you can just click this view button. We have a very nice viewer supported by 3JS, and it will show you all these print results. And also, if you click on this download optimization log, it will show you all those 100 orientation we evaluated to find the best orientation for you. So you can also change the parameter for your support structures. You can see that you have some teeth at the top, teeth at the bottom. You can manipulate all those parameters to change the teeth structure. If you want to make it stronger, you can make sure the penetration in the part is larger. And also, if you want to make it easier to remove, you can make the size of the support smaller. And we have some default values here. Those values are based on our experiment performed at iTemco. We want to make sure the support is strong enough and also easy to remove. And right now we provide 2 different types of support. One type is this lattice structures, you can see, and the other type is this cylinder type of structures. So this is what's happening in the back end. So we have 3 parts basically: the front end, back end, and the core algorithm. The front end, you basically input all those parameters, or material, printer, and after you click on the Start Job button, the backend, which is powered by Amazon Web Service, will create a computing environment for us, and then we will run all our algorithms in that computing environment. When it's done, we'll send all the results to the front end. That's what you see, all those results. So we did lots of work to make our code run fast. So we do both CPU and GPU parallel computing. You can see there we use the Amazon P3 instance for computing. The P3 instance offers lots of GPU cards and CPUs for computing. And we test the results on those 3 parts with different complexity. And you can see that the blue line is the simulation time without parallel computing, and the red line is with parallel computing. The simulation speed decreased a lot after we implement this. So this is a case study. We want to try our algorithm on this rectangular bar. It's a very simple part. So this is the left side is the same part built horizontally. The right side is the best orientation and support given by our software. And you can see that for this part built horizontally, we get a 500 micron distortion. For this orientation, we only get about 100 micron distortion, and the reduction is about 76%. For this another part, it's the orthopedic part. You can see that we will build it horizontally. We will get a very large distortion, which is about 3.5 millimeter. And when we build with this optimal orientation, we almost get 0 distortion. This is another example. It's an engine bracket. We give you 4 different options, you can see. Although you run minimum distortion, we give you other 3 options. And for this part, we choose the minimum support volume option because we don't want support structures inside of this holes. And this is the part we printed. We print with this orientation and we remove the structure, the support structure very easily. We just use the plier to get it done manually. So it's very easy to remove. And this is the part after post-processing. So finally, we print this pattern successfully with the right orientation and the right support structures. You can see that the orientation is really important, and with the right orientation and right support, we can print lots of changing parts very easily. And if you are interested, you can just go to this website, Additive.xyz. You can get a free trial very easily, and you can also contact our CEO Chad and our Vice President Brent to get a trial license. I will take any questions.